All right, are there any questions from the previous lecture? So I'll as usual review the discussion of the previous lecture, and if there are any questions, please do ask as we go along. So today we're going to be talking about confinement at infinite coupling, or in short, confinement. So let me review lecture 17. This is not readable, my handwriting, but what did we discuss last time? We talked about asymptotic freedom in non-abelian gauge theory. So here's the non-abelian gauge theory written, the Lagrangian, written in Faddeev-Popov variables, I guess, using the Faddeev-Popov method. This is what it looks like. Here's a non-abelian gauge field, the standard action piece of it that you're familiar with, the Yang-Mills, right? 1/4 T of R, F trace of F mu nu squared. Then you've got charged fermions in principle, right? And these are covariant derivatives, of course. Psi bar, and there could be in some representation little r, for instance. That's the notation we're using. Then we have the gauge fixing theorem, 1/2 C del mu a mu of a squared. You hopefully remember where this came from. And then we had ghosts. The ghosts were coming from the expansion of the determinant that was non-trivial. The determinant was coming out from the following thing, that one in non-abelian gauge theory, to impose a gauge condition, we had to put a Dirac delta function inside the path interval, and to change, we had to make a change of variables in that Dirac delta function. Now we were dealing with matrices. There will be a determinant that popped out of the Jacobian of the transformation, and that determinant had the gauge field, the non-abelian gauge field in it. So we couldn't just discard it as an overall constant, as in the case of the abelian gauge theory. So we exponentiated, wrote it as in terms of the exponential of a path interval over anti-commuting complex fields that we call ghosts that transform in the adjoint representation of the gauge group. This is just expansion of the coming from the determinant. Yeah.
Is there a way in which you can arrive to the ghost field, the ghost to the Lagrangian, without path integration? Canonical quantization.
Oh, wow. So let me try to lead you in that direction. The answer is very complicated. We won't have time to discuss it, but I understand what you're talking about is the Hamiltonian picture. Here, what we're using is the Lagrangian formulation. You're asking about the Hamiltonian. Now, Hamiltonians in gauge theories are a little bit more nuanced and complicated. So these are constrained systems. So there is like a long story of this, and it's related to BRC, related to, it's a long story. But yes, the Hamiltonian formulation, non-abelian gauge theory, is where you would find your answer. And then there won't be ghosts, there would be constraints. Like BRC. BRC was actually a manifestation of that, right? So you have this you have this enlarged Hilbert space, and these operators that are just, like you have a condition for state to be physical. We did write that actually, right? We talked about when we wrote down the conditions for physical operators, we said what is related to ghosts, right? We did say that. All right. So here's a covariant derivative. It's del mu minus I G A mu A T R A. These are the generators in some representation, but for some reason I picked this to be little r. Because my fermions are in little r, representation of the fermions. And here's the field strength, non-abelian field strength. It's not gauge invariant. Then asymptotic freedom was the observation that when we calculate the beta function at one, or doesn't have to be at one loop, but we calculate at one loop, and beta function as a function of g, the coupling, came out to be a negative times g cubed. And this was crucial because it means that deep in the UV, the coupling is small, and the theory can exist as a theory that emerges in the infrared. But now it comes at a cost. The theory gets strongly coupled in the infrared. That's what we're going to be talking about today. So just the summary of the calculation that we did for the one loop evaluation of the beta function, we looked at the gauge boson self-energy. There were 5 diagrams contributing to it. The fermion self-energy, there was the good old diagram this that we saw in QED, a similar version of it as well. Boson fermion interaction, the vertex, here's the two, and then we had 3 counterterms. And importantly, as we said, this is a symmetry principle that even though we only have 3 counterterms, but all the divergences are captured using these local counterterms to arbitrary order and perturbation theory. We had a journal club about that. Okay, so the one loop renormalized perturbation theory that we in one loop renormalized perturbation theory, we computed the beta function. It took, well, as we said several times in the course, the beta functions are MDDM, right? And the only M dependence in renormalized perturbation theory comes through the counterterms, because the counterterms will pick up M dependence from normalization conditions, right? So here's the result of the calculation was that delta 1 gave you C2 of R and C2 of G. Do you remember what this was? Okay. So that's the vertex. Delta 1 is the vertex correction. And then C2 of R is the propagator of the fermion mass correction. And then here's the gauge boson propagator correction. Once all the dust settles down, what we found is that the beta function of one loop is minus G cubed over 4 pi squared, 11 over 3, C2 of G. G is the adjoint representation, so C2 of G is, for SUN, N, minus 4 over 3 NF T of R. If I pick R to be fundamental representation, it is half, exactly. So just the conclusion is that if NF is small enough, beta function at one loop remains negative, and we have asymptotic freedom. Questions?
What was NF again?
Sorry?
What was N to F?
NF is the number of fermions. Do you remember where it comes? It comes from here, this diagram. The fermions are in the loop, and it comes with a negative sign. All right. We came up with a physical interpretation, or physical way to think about why the beta function went from positive to negative as we went from QED to QCD, for example, or non-abelian gauge theory. In QED, the physics intuition behind the coupling decreasing at long scales is charge screening. The coupling of QED, alpha of QED is E squared over 4 pi. So what we're dealing with is the charge of the electron. What does it mean for the charge of the electron to be renormalized? What it means is that, well, you have an electron sitting somewhere, you look at the potential. We did this exercise actually in QFT1. You look at the potential. The potential at tree level is alpha over R, right? That's just E squared over 4 pi R. But when you start doing one loop calculations, what it means is that you're taking into account the effect of pair creation of the vacuum that will create a cloud. This is just cartoon picture. A cloud around this, now that will effectively change the potential at large distance. How does it change the potential? Here's how the potential is changed. We calculate this change due to the one loop dipole contribution. So that the vacuum fluctuations, this is negative charge, will basically create pairs and anti-pair, electron and anti-electron pairs, positron pairs, and they will align this way. Now, this is a dipole. It creates a dipole that reduces the electric field, right? And this is charge screening. This happens all the time in materials, right? This happens. This is very, very common in QED. In non-abelian gauge theory, what we have is charge anti-screening. So keep this picture in mind. So what we're going to do, what we're going to say is that we first put now a non-abelian charge at some point. We're going to see the effect of that on vacuum fluctuations around it and see how they contribute correcting the initial charge. We're going to put now, let's say we have SU2. So your charge is rho 1, rho 2, rho 3. Let's just say we put some unit of rho 1. What is the field equation we're trying to solve? So if this were abelian, this would be the field equation, right? This is just a Coulomb law, right? This is the 1 over square Coulomb law. So you put this here, and this is the first line, right? Rho 1 G is the divergence of E1, right? E1 going with rho 1. But then because it's non-abelian, there's this extra term. FABC is epsilon 1, 2, 3, because these are the structure constants of the adjoint representation, right? It's SQ2 adjoint representation. So this is what it looks like. So let's just write down the equation for E1 and E3, for example, right? Because I didn't put an E3 charge, so this is 0, so I have to simultaneously solve these two. If this is not there and this is not there, the answer to this is going to be 1 over r squared. Now, first start here. First start here, ignore this term. Because there is rho 1, there's some E1. Now, because there is E1 and there are vacuum fluctuations of A2, there will be an effective E3. But that effective E3 comes with a minus sign. It's as if there is a tiny negative rho 3. Right? This is the dipole going on, like it's as if there's a tiny negative rho 3. Right? But now here again, E3 comes up and sits here. So this effective negative E3 charge will come here. So you have to be careful with your dot products. But once you keep track of the dot products, this term, what does it do? Can you see what it does? It adds to it. It precisely adds to it. So here's my attempt at showing this. I know it's a busy picture, but the line of logic is this. First, ignore this term. We create and roll E1. Put E1 in here. You observe that you have an effective negative rho 3. Put that in here. You pick up a positive contribution, and that means that you have an effective charge. Where does this extra minus sign come from? Can you see it? It comes from epsilon. The fact that here is 2, 1, that is reverse ordering, and this is 1, 2, 3, that is correct ordering. So this is plus, this is minus. That's how it comes about. This is the origin. So now this leads to anti-screening, right? This leads to anti-screening. This is just the contribution of this is the contribution of the non-abelian gauge fields, right? So here what we're talking about, this is the contribution of the fermion loops, right? This is a fermion loops contribution because there's nothing else. So this is present in QCD as well. Fermions do screen your charge. However, the gauge boson itself anti-screens. So that's why if NF is small enough in this competition, the anti-screening wins. You have beta function that's negative. Right? That's the origin of this. But that if an NF is 0, you're always going to have anti-screening. So Yang mills exist. Very cool. Yeah.
The charges are what for SU3? Which one is the charge? Which one can we say physically is the charge?
What do you mean?
I mean, for U1, we say that the charge is the electric charge.
Mm-hmm.
Then for SU3.
I'm not sure what you mean.
Like what
You're asking what are the excitations of the theory?
No, what is the charge? What is the coupling constant?
You're asking what are the excitations of this?
Okay.
That's what you're asking.
Why?
The excitations of the theory. Is it clear why?
Why I'm asking that now?
Yeah. So first of all, even in the case of QED, the objects that are physical, we're actually going to talk about this in a second, right? I'm actually going to talk about this in a second, but well, we'll see. You'll see. You'll see. The question you're asking is, what are the excitations? If I don't answer it, bring me back to it, okay?
Sorry.
Background gauge fields. We talked about, well, we use background gauge fields as an effective action method to derive the beta function in a very quick way, right? So what is this? We take the gauge field and say there's a background and there's some sort of fluctuations. Now we define the covariant derivative with respect to this background field. So for example, the covariant derivative will take this form, right? Now this is the background field. This is the covariant derivative. So now this is the full thing, right? So the fermion term will be the background fermion term plus an extra term. And then the field strength will be a background field. Well, these are fluctuations, but with covariant derivative of the background. And then these are the extra terms, right? Why are we doing this? Because, sorry, this is the gauge invariance. Now, what is important here is that because A mu is not physical, your partition function. So what are we calculating? You're building some sort of background gauge field or effective action. Effective action. You have these gauge fields that are background gauge fields. This is not a physical thing, right? This is not physical. Why is that? Just for a second, think of QED. In QED, you could talk about the effective action in some background electric or magnetic field. A mu is not electric or magnetic field. A mu has electric and magnetic field and junk next to it, gauge dependent stuff. So if you calculated an object like this, if it's supposed to be a physical thing, it better be gauge invariant under gauge transformation of a bar. Because the only thing that's physical are the only physical thing is turning on a gauge invariant background, magnetic or electric field, right? In the non-abelian case, it's the same story. So you should have gauge invariance for effective action with respect to gauge transformation of the background field. We can use this convenient choice of gauge, also motivated by the background gauge field. Now the Fedya-Popov Lagrangian looks like this. I'm not going to bore you with it. We went through this. What we did was we calculated the effective action of one loop by taking this Fedya-Popov and expanding to a second order fluctuation. Now, if you expand, this was our method in general to calculate the effective action of one loop. So of course, at one loop, you're gonna get a term that looks like the field strength of the fluctuation with respect to the background covariant field. You're gonna get the background field strength next to the fluctuations. You're gonna get this gauge fixing thing, but now this is in the background. You may saw we did integration by parts and rewrote this in a way that looks like what we wanted to do is that we wanted to write it as a path integral of e to the power of a fluctuation, some operator a, right? That's the Gaussian piece we wanted to abstract out. And here's the form it took. So there was a piece that was purely differential operators, right? So this is the d bar squared, and these are the differential operators. And there's a piece that's like we wrote this way. Then there was an observation. I understand it was too quick, but you have to work out the details that we massage this in the following form. This is the background field strength that contributes to the kinetic term, if you wish, of the fluctuation. In the case of when we had the scalar field theory, just to recall, when we introduced background fields, the presence of the background fields shifted masses for the fluctuations, right? We ended up with a mass matrix in the OM model, and the mass depended on the directions that we were doing spontaneous image breaking. Here, similar thing happens. The background field strength appears in the kinetic term, as it should. And then, well, here's what was FABC, and I use the trick. I use the trick, there's a simplifying trick. You could go through them one by one, term by term, because in the Lagrangian, Fourier-Popov Lagrangian, there are all sorts of terms, right? You could go through them term by term, but here was what I told you, that you could always repackage, the contribution every term could be repackaged in terms of this form. And then the term that has to do with the background field strengths is sitting next to this generator of the Lorentz transformation for the corresponding field, depending on the spin and the field. So for example, if when you look at the spinners, the result is going to be minus d bar squared plus 2 or half, blah, blah, blah. This is the Lorentz generator for spin half field. You put all of this together, there's this covariant background field D'Alembert we can define. I'm basically giving you all the ingredients for how to write down effective actions for various types of, like non-abelian gauge theories coupled to various types of matter at one loop, right? I'm just giving you the answer. Notice that it's all calculate is coming from the Gaussian piece of the fluctuation, right? That's the beauty of effective action. It's all coming from this. So of course it carries it depends on the representation of the matter field, lil r, could be anything. J is the spin. So it depends on the spin of the representation. So this is space-time representation, and this is our representation. Could there be mass? If this is supposed to be the Lorentz part of the representation, could there be mass? Huh? Mass?
No,
What's wrong if I add masses?
breaks gauge.
It breaks gauge symmetry. How did we get massive? Well, no, we haven't gotten that. Sorry. Whoops. We have to go through spontaneous symmetry working to give masses to our fermions. Gauge theory. We'll see that. We haven't seen that yet. All right. So here's the effective action. It's basically the piece that is the background plus counter terms, because you're doing renormalize one loop, renormalize effective action. And then the contribution of the other terms are just a bunch of determinants, right? This is minus half delta of G1 because it's coming from what? It's a spin one gauge fields. This is the gauge bosons. Minus half because these are bosons, spin statistics. Determinant of delta R half to the power of NF over 2 plus half because these are fermions, right? Spin half, spin statistics in some representation R.
Why half? If there are anti-commuting, shouldn't there be any half?
Sorry.
Shouldn't there be any half?
Shouldn't there be? These are fermions, so they're spin half particle.
Yeah.
Right, and then spin statistics theorem tells us that they're anti-commuting.
Yes.
So spin half must be anti-commuting.
Yeah, wouldn't that make just determinant of the thing, not determinant to the power of 1/2?
No, the half. You're talking about this half, not the plus.
Yeah,
or the minus. I think it's about complex fermions. If I'm remembering
This is the
correctly.
plasma.
Yeah, but these are complex fermions. These are complex fermions. Yeah, this is sorry, no. Not complex. These are real fermions. Right. Yeah. Wait a second. What are we path integrating over? We're path integrating over this guy. Yeah, I think that's right. If it were complex fermions, it should be. Wait, is this a Dirac? Yeah, if it's Dirac, it should be half. Well, I'll fix that. I'll fix that. I don't quite recall. But there's a half for sure. In QCD, for example, there's a half. All right. Okay, so and then there's this is the ghost. Nobody complained about spin statistics for ghosts. right? Their spin's 0. They're anti-commuting. Does that bother you? The origin of spin statistics, if you go back to it, it had to do with, it's a physical statement about commutational relations, right? It relies on the fact that you're talking about observables. These are not observables. These are just exponentiated terms. So they're not honest to goodness particles because they can never be external legs. They can never contribute as external states. They're not. They're just there to keep track of the numbers. Just extra, it's keeping track of overcounting. It's removing the overcount. All right. So there's this determinant. Of course, there are divergences all over the place, so we have to renormalize it. And instead of doing one loop renormalized perturbation theory with these counter terms, a quick way that I did it was Wilsonian framework, where you basically integrate from some cutoff lambda to some m. And then basically what you do is, here is the initial theory at some g squared of cutoff lambda. And once you integrate all the modes between some cutoff lambda and some m, this is how it should change. And you call this new thing the new coupling, right? 1/4g squared of m. So to do that, we have to extract, take out the piece of these logs that look like this, right? So we did that, and actually there's a formula we wrote down that depends on the representation is spin. And you just, once you have that, you can literally write down the contribution of the one loop, these log determinants to the running of the coupling, and this is how the coupling changes, right? These guys capture the change of the coupling. As expected, these are just beta functions, right? Finally, once all the dust settles, beta function becomes half of C tilde G1. This is the gauge field boson, gauge boson. This is the fermion, this is the ghost. These are the fermions, right? And GQ. For this to be asymptotically free, this coefficient has to be negative, right? But these coefficients are these C tildes are completely fixed by representation theory. TR over 4 pi squared, third for scalars, minus 8/3 Dirac spinors, minus 20/3 4 vectors, right? So importantly, the gauge boson is the thing that we're putting all our bets on, comes with a negative minus 20/3, so that's a large number, that's good. You put all of them together, you get a bunch, you cancel terms out, you get minus g cubed over 4 pi squared, 11/3 C2 of G minus 4/3 and F of TR. Strong nuclear force, G is SU3, Tn is half, fundamental, anti-fundamental. Here's what it looks like, the beta function. For NF small enough, it's negative. What is NF is in QCD?
6.
We'll get there. In an asymptotically free theory, what the result of this, I can write it as minus g cubed over 4 pi squared, a positive number b. This is not to be confused with the b I used in the past. M is b lambda, right? It's just positive number b. It's, as we've seen before, it's more convenient to capture everything in terms of alpha squared. So here it could also define the alpha squared parameter as a coupling of the theory. Then your alpha at scale mu is alpha at scale m divided by this. This is the coupling, running of the coupling. Sorry. Thank you. Now, there's something funny that happens. So m is some initial scale you start with, and you bring it down to mu. This term is negative. So what happens is that as you go towards the infrared, the coupling grows, and the one loop calculation suggests that you have a Landau pole at this scale. At this scale, once you hit the scale, the coupling is gone to infinity. Now, this is of course like just this is not to be trusted. It's a Landau pole, right? It just means that you're doing one loop calculation and then other loops are going to be important. It was complicated, but it's a hint that, okay, now we survived the UV. The theory is UV clean, but it's deep in the infrared. It's a mess, right? Non-abelian gauge series, Yang Mills strongly coupled in the infrared. The scale that this blows up, the theory is going to be so complex, so strongly interacting that talking in terms of the initial degrees of freedom that we put in the Lagrangian is silly. We've talked about this in the past in quantum field theory, right? When the degrees of freedom of the UV, if you flow non-trivially towards some sort of infrared, complicated infrared, might have nothing to do with the degrees of freedom of the infrared. We've seen this before, right? So the degrees of freedom that you're going to see in our nature are not going to be quarks. Quarks are not going to be the fermions and let's give them names. The gauge boson for QCD, we're going to call it gluon. We're going to call the fundamental matter fields fermions, we're going to call them quarks, right? We're not going to see at low energies that we are. First of all, we have to figure out at what energy scale the theory becomes strongly coupled, right? And then we go talk to our nuclear physics friends. What do you see? Do you see any quarks or gluons? No, they don't. What do they see? They see pions. There are a bunch of particles. They've listed their spins, properties, masses. There's a big chart. And it seems like QCD is going to struggle to generate these numbers. We'll have to do something harder, more complicated. Do you have a guess what we're going to do? What do people do in nuclear physics? Well, they're balanced, but how do you find them? Perturbation theory is not going to get you far. Lattice gauge theory. We put those on lattice. So these are like Monte Carlo hardcore calculations, and they match what we see. But the evidence for QCD came from high energy physics, right? So we looked at high energy scatterings, and then we discovered quarks, and we discovered all of those guys at very, very high energies. The theory is weakly coupled. But in the infrared, still somehow the non-perturbative definition of the theory that we lack at the moment, but somehow the lattice gives us something, should be able to reproduce using Monte Carlo brute force calculation of path intervals, some of the numbers we see in nuclear physics. And it is successful. Partial, well, up to the point we've tried. These are very difficult calculations. Now, what happens? For a second, imagine G goes to infinity. What does that mean? What was the effective action like? It was 1 over G squared integral of blah, blah, blah. When G squared goes to infinity, this means that your action is 0. What does that mean? It means that, what was the role of the action? It was e to minus s as the weight, the contribution of particular field configuration. When action goes to 0, it means that any field configuration is as likely. Everything is equal likely. So what we're going to be doing is that we're just going to do Haar random intervals. Are these words familiar? What are the degrees of freedom we're integrating over? These are gauge group elements. So SUN. They are SUN matrices, n by n unitary matrices. If you integrate over the space of n by n unitary matrices with a uniform measure, it has a name, Haar measure. So these are Haar integrals, and you're gonna work them out in a homework problem. So this lecture ends with a calculation that your homework is going to be reproducing. Okay? That's the infinite coupling limit. That's the infinite coupling limit. That's hence the title of the lecture, right? Confinement at infinite coupling. Questions? What are we doing? Think about this a little bit. You could think about it this way. In a theory that is perturbative, there's a particle propagating from this point to that point. There is an amplitude for any thing, any path, these paths are like field configurations, right? For 0 plus 1 dimensional PFC, right? And but because of the action, there is a saddle point. So this is where the action is minimized. This is dominant. All the other contributions are oscillating so wildly in phase that they cancel or they do not effectively contribute, right? So everything comes from this guy and expansion and the expansion around the this is like it's a saddle point, right? This expansion of a second order around this will pick up a determinant. And these are quantum effects. If so, here your action is e to the power of I s over h bar. H bar is like effectively your coupling. If h bar, right? If h bar goes to infinity, that means the quantum fluctuations are large. They wash out all the classicality. When coupling goes to infinity, it means that anything is as likely, any configuration is as likely as that. There is absolutely no sense to saying that, to talking about a classical thing, right? That's what the physics is. And what's the analogy with finite temperature statistical physics, statistical field theory?
Transition.
No. What is the same limit in statistical field theory? Infinite temperature, beta going to 0. Right? Because over there is you're dealing with beta minus beta h, right? Beta sits outside the path of right? Beta goes to 0, that's infinite temperature. That's equipartition deep in the UV. Right? It's infinite temperature. Question. So that's what we're going to be discussing. Now I'm going to give you some, of course, confinement is a very, very deep problem. We don't understand it. We don't have a physical in principle description of it. It's a millennium problem. We don't, to show that given Yang Mills, it confines. Nobody knows how to show that. We haven't shown that. We just do one little calculation, right? But there is a lot of physics as physicists we still know. So what I'm going to do until the end of this lecture is to give you physical picture. Where does this physical picture come from? It comes from this hard random intervals, right? Now I'm taking a little bit of departure from the microscopic definition of quantum field theory. I'm just going to be basically basing most of my intuition on the lattice, right? Actually, that's going to be mostly your homework, but I'm going to argue towards that. All right. Sorry. All right. Now, we get to your question. Confinement. Here's a definition for confinement. It's a colloquial definition. A gauge theory with matter is confining if all finite energy states are invariant under a global gauge transformation. Don't tell anyone I use these words. What do I mean by global gauge transformation? That's almost an oxymoron. A gauge transformation was sending psi of x to e to the power of I alpha x psi of x. I'm just saying take this alpha to be independent position. Good. Now, a theory is confining if all finite energy states transform are invariant under this. Good. What is not invariant under this? We don't need to look very far. This, psi of x. Right? Isolated charged particles, fermions, are not invariant under it. Therefore, one consequence of this definition is that fermions, an individual fermion, should acquire infinite mass, infinite energy to create. The single fermion excitation should cost infinite energy, so it should be outside the Hilbert space. Another way of saying is that charged states, electron of QED, if they have finite energy, the theory is not confined. right? Does that answer your question? Good. Do you see an alternative way of rewarding this? So this is a really awkward way of putting things. Can you give this a symmetry picture? Symmetry interpretation. When this happens, what does it mean? There is a global symmetry, right? Because the theory now, whatever it is that remains, what are all the fine energy excitations are invariant under this transformation. So there's a global symmetry. This is a legit global symmetry, right? So there's a very group theoretic symmetry interpretation of all of this, of course. Now, just building intuition, what happens? What does it mean when we say that it costs infinite energy? So what does it mean? Now, we're dealing with a gauge theory. So a single charge, right? A single charge is, let's say, charge Q, is not a gauge invariant object. It's not physical observable. What is a gauge invariant object?
Charge preserved.
Volume QED. Give me an example. An electron and a positron, okay. But so it's not an electron and a positron, it's actually a Wilson loop connecting the two. That's a gauge invariant observable, right? Because if you have psi of x, psi of y under gauge transformation, this psi bar, this will transform as psi of x, u dagger of x. This guy will transform as psi of y, u of y, won't be gauge invariant. You need a connection. I mean, you just have to have a way of comparing the gauge transformation at 2 points. And that's what the connection does for you, right? So you did Wilson loop. That's why there is a line that connects the two. So what does it mean to talk about a single electron? The single electron is attached to a Wilson line that goes all the way to infinity. What is the energy, potential energy of a single electron that we calculate in E&M lecture 1 or 2? It's a statement that how much does it, like how much energy does this single guy have? That's what it is. It's just like, imagine this was minus Q and taking that to infinity. That's what it is. That's actually literally how you calculate it. You calculate the force that you feel after you stretch this, which is a tension of the string, and you just integrate this all the way to infinity. Right? That's what the calculation meant. So what is going on? What's going on is that, well, here's an excitation of the theory, it's gauge invariant. It has an energy, and there will be a length scale associated with it. Try to stretch it. So there's an energy cost for this configuration. Keep stretching this, right? The energy will change, right? And if the point is that if the energy, I guess the tension of the string is so much that it costs infinite energy to pull this to infinity, then you will never going to see a single electron. You're in the confined phase, right? That's the confined phase. Now, what does it mean? Like, so what is the physics of it? What exactly does what's the physics of this? What happens is this, if you keep pulling on this string, at some point the string will snap. Physically, this is what's going to happen. This physics will, the string will snap and you're going to end up with this. What is that? That's pair creation of charge from the vacuum. That's the physics of it. What is that energy scale? That's the energy. That's when. So this picture that I was saying that you pull this to infinity. That was a very classical picture. Remember when we motivated quantum field theory? One of the main motivation was that the quantum field theory is that has to be a multi-particle system. This is a single particle system. That's why it gets things wrong. What happens in quantum field theory is that once you stretch it, once you the energy cost of this is equal to m squared, or m squared, enough to pair create, there will be pair creation. Right? If you pull this enough, it will pair create, and this is the physical picture. Yeah.
So in QED, we have a single electron.
Mhm.
There is a loop extensor to into it, right? By default.
A
That's
single electron, that state is what you're describing. Yes,
okay.
that's the state. I mean, the theory has all sorts of excitations. One of them is that, and that's what the gauge invariant description of that is a line going all the way to infinity. But notice that there's absolutely no meaning to the statement where the line is. It's just a line going to infinity.
Right. What infinity is with it.
What? No, it's important. It will, the meaning of where the line is becomes clear when you put other charges. Now the relative position of these Wilson lines, there's some physics associated with it. This is a little bit of a complicated topic. I think I say too strongly. There is, what I should have said is that when you take the electron and attach it to a line, that line you draw it somewhere and give it some configuration. There is gauge dependence in that picture. You know, that's all I want to say.
Are those infinite Wilson lines observables? I mean, you place an electron.
Observables are gauge invariant.
Okay.
Wilson loops are observables. Wilson lines that end with charges are observables. I don't know of any other ones. Good. All right. So I just said this. Wilson loops are observables. I'm gonna play a little bit of a trick. I'm gonna mix and match things from Euclidean path integrals because it's very helpful actually. In non-abelian gauge theory, trace of a Wilson loop, well, a Wilson loop is a trace of the path-ordered exponentiated integral, this guy, right, of the gauge field. Okay. So imagine a path, this in Euclidean time, a Wilson loop in Euclidean time. Actually, let's first take it to be a real time, right? So here's a Wilson loop, and this is the time direction, and this is space direction. Let's just focus on the initial state. The initial state, it looks like a charge, anti-charge, connected with a Wilson line. So this looks like this, looks like this. Then it evolves in time for a while, same distance. And then at this point, they annihilate. So you create this pair, you evolve in time, they annihilate. If this is real time. Or alternatively, I could take this state. This is the initial state, evolve with the Euclidean time. Take the overlap with this. This would be a Euclidean Wilson loop. This is the Euclidean Wilson loop. I'll be talking about the Euclidean Wilson. Why am I talking? There's a reason for that. Everyone's with me here? Now, here's a good exercise for you to remind yourself of Euclidean path integrals. If Euclidean time t is much larger, I'm just picking a very simple geometric configuration, right? Like a rectangle. If Euclidean time evolution t is much larger than the distance between the charge and quark antiquark, in that regime, e to the power of th is well approximated. This guy is well approximated by e to minus t energy of the pair. Do you see that? This is I don't think I literally put it in your homework problem, but it's a good exercise right here. You just have to go back to your twin path integrals, what we were doing, or maybe you can just see it here. But that's what it is. It's e to minus t energy. Do you see it or not? Okay. All right, that's good. So here's an observable. And here's its interpretation in this regime. So confinement was all about the energy of the pair. Right? So it will be this language translates this to, so, okay, sorry, let's back up a little bit. Deep in the UV, the theory will have single quark excitations. At some point, you will undergo a phase transition, confinement, deconfinement phase transition. The high energy physics is called deconfined. There are free fermions, right? Well, they cost energy, but they exist as finite energy excitations. And then you undergo a phase transition at some point. The physics will be described using new degrees of freedom. In this new physics, you're in a confined phase. There's a phase transition. The question is, what is the order parameter for this phase transition? What I'm trying to argue to you is that this Euclidean Wilson loop is an order parameter for the phase transition. Why? Because we just said confinement to confinement, one way of talking about it is about the energy of the pair. Right? Okay. Good. Everybody's with me? So first, well, actually, the way I'm going to do it is a little bit mean, but I'm going to calculate for you this in perturbation theory. Meaning what? Meaning deep in the UV. When the theory is deconfined, I'll see a behavior. Then I'm going to tell you in your homework, you will have to calculate the same thing using lattice integrals over Har-random integrals, infinite Har-random unitaries, the infinite coupling limit, the same Wilson loop, the expectation value, the same Wilson loop, and you'll find another behavior that I'll also say, and that the behaviors will be giving you the phase transition order parameter. So what is the story? Again, the expectation value of this Wilson loop is going to be an order parameter for the confinement phase transition. And here's what the observable is. So there's a path integral you're doing over all field configuration, e to minus s, because it's Euclidean, e to the power of I s, this is generated. In the homework you're going to be doing, the difference is that you're integrating over these guys. This is not there. Right? That's all. All right, so what is this Wilson loop? This Wilson loop is pretty easy to calculate in Euclidean space. Why? Because in Euclidean space, you don't need to worry about ordering. Right? So you have an integral of a here and a here. There are two integrals over a's. So you have to integrate over the 2-point function. There's a double integral over x and y. Right? So here's a propagator. There's an integral over a loop for x. There's an integral over a loop for y, and then 1 over 2g squared. Good. You might be. Are you confused about this g squared or parameter or not? It's straightforward. It should be there. I'll leave it to you. Yeah. Okay. This is what the Wilson loop is in this simple thing. Of course, I have to integrate it in this particular geometry I'm talking about. But this is a true statement for any Wilson. No, that's good. That's good. So basically what I'm doing is I'm inserting this inside the path integral. I'm treating integral of dx mu over gamma as if it's a source. That's what I'm doing. In QED, the 2-point function, the propagator is just delta mu nu, right? This integral. It's x minus y squared. That's the only thing it can be because it's a massless mode, right? That's what it has to be. All right, that's good. So let's plug it in. It's x minus y squared. You have to integrate here, this bit and this bit. When you integrate it here, you're integrating over the 2-point function, bring them close. There will be contact term. There will be the UV divergences from here that I'm going to regulate this way. Right? And then there will be a piece that's about the operators that are separated from here and here. Right? And that gives you 2 pi over r. You could do this calculation, it's pretty straightforward. You will do it. The Wilson loop, the answer is going to be, there will be a divergent piece, but I'm telling you where it comes from. It comes from this part, the UV divergence when the charges are coming close to each other. And then there will be this bit that has to do with the keeping these charges distance r away for time t. That's the energy cost of it. Right? Not quite, but like it's related to the energy cost. And then there are corrections to it, which are log 11t. All right, so we said that the expectation value W of R in the large T approximation is interpreted as the energy of the pair. So here it is, the energy of the pair is alpha over R with a minus sign here, 2 alpha over pi epsilon QV. Is this familiar? This is just a Coulomb law in QED. We haven't done much. This integral is precisely without, this I motivated using Wilson loops, all of that, but this is again the same integral saying that start with charges, right? From actually it's turned around. Bring charges from all the way from infinity to some finite distance, right? This is one calculation that will give you this part, this 2 pi over r. And then the other part is about starting, the divergent piece comes from starting with charges that are like on top of each other and separating them. That involves infinite energy. Charges that are infinite, like just sitting on top of each other, they will have a lot of energy. Good. This is a divergent self-energy that's there. Questions? Is it clear why I put corrections that are ln of t? What are these corrections going to correct? They're going to correct the potential. Just a few slides up, I had the potential of QED corrected due to one loop corrections when we were discussing the running of alpha. If you look at that, you'll conclude this has to be element.
Sorry, can I see the equation for the Wilson loop? Yeah.
This one?
Yeah, so
Oh, here.
no. So what you have below is just exact computation. I mean, it's literally the result of that integral.
In QED. In QED, yes.
Okay.
Literally.
There is not, okay.
This is in QED. It can't, the calculation is not going to be easy in non-abelian gauge theory. Right? Why? Well, there are self-interactions. Why can I do this integral in QED? The theory is free. These are Gaussian integrals. Right? Whereas in non-abelian gauge theory, the theory is interacting. So I'm not going to be able to do these integrals. I'm going to do approximations in my next slide. Good? QED is a free theory, so I can do these Gaussian integrals. That's how I did it. Or whoever I copied this from. All right. In non-abelian gauge theory, there are interactions. Just exactly what I was saying. So we have to expand in powers of G. Right? Here's what you get if you expand to the lowest order in G. There will be G squared. Of course, there will be multiplicative factors that are coming from the representation theory. Right? And then the propagator is this. There will be similar integral, blah, blah, blah. Right? I'm expanding the exponential. I'm just expanding exponential and looking at the first term. All right. The important part of this was the following, that the Wilson loop is proportional to what exactly? It's the Wilson, the energy of the pair, I guess the message was that the energy of the pair is 1 over, is alpha over r, right? Plus a divergence. That's the thing that I wanted you guys to get. And the same calculation will reproduce in perturbation theory in non-abelian gauge. But this is perturbation theory, so this is deep in the UV. Now, what you would be doing in your homework problem is to think of the same calculation, but now at infinite coupling. At infinite coupling, we don't have a path integral understanding of things. We have lattice gauge theory, right? So in SUN gauge theory, you start with a lattice. On each edge, you put a degree of freedom. Each edge, you put a connection, right? And that connection, you think of it as, there's a U acting on each vertex. And these guys, you view them as elements of the group, right? Some elements of the group. These are SUN matrices. That's why I'm labeling by a point. So I'm labeling an edge by a point where it starts and a direction that is pointing out, right? Traversing, going in the opposite direction is U dagger, right? Why is that? Because it's a connection, right? If I start at this point, go here, come back, it should be identical. So if this is U, this is gonna be U dagger. All right, so what's the action? The action is that to every plaquette, I'm gonna first traverse it this way. So trace of just multiply these guys, right? Plus the Hermitian conjugate. Hermitian conjugate inside the traces means that W of plaquette plus the W of plaquette in the reverse orientation. You do that, you expand it, you get trace of F12 squared. That's basically the origin of the Yang-Mills piece of the action. So this is what it looks like. So the action for this theory is minus 1 over 2g squared, sum over plaquettes, the W of plaquettes. Of course, when g goes to infinity, this action is not there. But then when this term is not in the is not a weight term, what are you doing? Your path integral. So this path integral becomes a path integral over all unitaries with Haar random measure. The homework is about what does it mean to talk about a Haar random measure. So U1, what is that group?
That is just.
What is it? Describe it. Like geometrically. It's a circle. What is a uniform measure on a circle?
R theta.
D theta. Theta runs from 0 to pi, right? SU2. SU2 is a double cover of S3, three sphere, right? So there's a measure on it. What is it? It's exactly the same measure as the uniform measure on S3, right? But the double cover. So the volume is multiplied by 2. For every SUN, there's a uniform measure. It's called Haar measure. Do you guys know the definition of Haar measure? So Haar measure is the unique measure on these Lie groups that has the following two properties. That it's both left invariant and right invariant. Because when you talk about the action of the group, you have the action of acting with the group element on the left or acting on the group element on the right. Right? It's the unique measure which is both left invariant and right invariant. Now, it's a question for you guys to come up with a group example where you have left invariant measures, different right invariant measures, and Haar measures. There are some important examples of such things. All right, good. But this is the content of your homework. Anyway, in your homework, you'll see that as g goes to infinity, s goes to 0. So your path integral becomes a path integral over Haar random integrals. So on every link, you're putting a SUN random matrix. And you'll have to integrate over these guys. And a Haar random measure means that integral of du, uij is 0. Why? Is it clear what left invariant and right invariant means? When I write du, what does it mean to act on the left on this measure? Pick a particular unitary v, then you can talk about dvu. So when you want to talk, this was particular u in an SUN. before talking about this measure, first apply a V and then associate, right? That's like a rotation on SUN, right? Then you could also talk about D of U, V dagger, left invariant, right? Left invariant or right, left invariant means this. Right invariant means this. Now, if you're dealing with a hard random interval, and you have left invariance and right invariance, what is this interval? Convince yourself this must be zero. Anyways, for you. This is going to be homework, actually. Figuring out these moments. It's a very important exercise in physics, and you'll see it over and over again, hopefully in your research. Okay, so what is the outcome of your homework problem? Is that at infinite coupling, as a matter of fact, no, actually, you'll see that at large coupling, so there is something that's called infinite coupling perturbation theory. There is something called infinite coupling perturbation theory. You have a sense of it, do you? Okay, maybe not yet, but hopefully after we do homework, you'll get a sense of it. This becomes 1 over G squared to a power of area over epsilon UV squared. This is going to be e to the power of energy of the pair, T. Good? So, when the energy of the pair is proportional to the distance of the pair, this is a linear potential between non-abelian point charges. You're in the deconfined phase. Right? In this case, how does the energy scale? Oh, sorry, I misspoke. In this case, the energy scales like RT. The energy scales like R, right? So if it's proportional, it's a linear potential, you're in confined phase. In the perturbative case, how does the energy scale? 1 over R. I misspoke, sorry about that. Right? So that's the distinction. Now, you are probably familiar from your basic classical physics with systems that when you like two mass, like two pieces of mass attached by something, but as you separate them, the energy grows linearly in their distance. Or maybe you're not, but this is what it is. This is what this object is. All right, so this is the end of this lecture. In summary, what did we talk about? We talked about non-abelian gauge theories. We showed that we had indications to believe that they confine, or we had indications that we saw that the beta function is negative at one loop, and then that was indication that the theory is clean, is trivial in the UV, but in the IR the coupling grows, and we were interested in knowing what happens. The belief is that the theory confines, right? This belief is based on just opening our eyes and looking around, but also based on a lot of calculation and matching different things. The theory confines. What I want you guys to understand is that there's a phase transition from deconfinement to confinement. In this phase transition, something really funny happens. Well, we talked about the Norder parameter for it, right? Which is the energy of the pair. The thing that is, I want you to realize is the following. Maybe I will comment on this, maybe I don't think I will comment on this. The Lagrangian that you put in the action, right, didn't have any mass scales, right? There was no mass scales. It was classically scale invariant. Now, how would you ever, by massaging a path interval of this form, calculate out of this the energy scale at which the theory confines, the phase transition energy scale. For the theory to undergo a phase transition, there has to be a temperature and energy. The energy scale when the theory confines. Above it, there are free particles found, and below it, there are free fermions found, and below it there are none. There's a dimensionful parameter that has to come out. But in the path integral, the Fedorov path integral, there were no energy scales. So this is a brand new phenomenon. There has to be a dimensionful parameter coming out of the interval. This is one of the crazy elements of why this is such a difficult problem. This phenomenon is called dimensional transmutation. Quantum effects must invent a scale for you, a dimensionful parameter for you. It will depend on h bar, of course. That's the only thing that we've got, right? So it's a purely quantum mechanical. The phase transition is there because of quantum effects, right? This is a little bit different from what you might be, or yeah, it's called dimensional transmutation. The scale of the scale of the transition. We have absolutely no clue how to calculate this from first principle. Well, actually, that's a little bit of an overstatement. At this level, we have. All right. Okay. Are there any last questions?
But the phase transition was calculated from the coupling G square.
Well, that was hinted at. There's no calculation there. You know, we did calculate. You were talking about the Landau pole. Well, Landau pole is just like a silly calculation, right? You do calculate something at one loop, you take it literally, and then it blows up at some point. You say, there's gotta be some non-perturbative physics going on. That's all it means, right? But it doesn't tell you about phase transition, has sharp definition, all of that. This is a hint. And then we have other hints. Well, most obvious hint is nuclear physics. Right? We look at nuclear physics, we do not find a single part, right? We find pions there. There's an effective field theory of pions.
Is there any way to understand these results without resulting to Wilson loops? Or are those?
Those are the observables of the theory. I mean, you want to hopefully talk about, I mean, there are other ways of describing qualitatively the phase transition. Often you have to resort to theories with more symmetries, like supersymmetric theories or something where you can a little bit more handle. And still in all of these, it's very hard to establish something. There are holographies helped a lot. There's like some picture coming from holography. If the theory is holographic, you know, like for specific theories with extra symmetries and extra properties, we've better understanding. But as physicists, you know, like if you can't solve a problem, solve an adjacent simpler problem. That's what we've been doing for a very, very long time. I don't know what the answer to the question. I don't know.
This is all to understand the strong nuclear force. All of this is.
Sorry, say it again.
All of this is just to understand the single nuclear force.
Yeah. But I mean, it's not to we gotta appreciate the fact that lattice gauge theory works like far. It works. Lattice gauge theory, as far as we pushed it, it gets numbers right. And these are like crazy Monte Carlo, obscure, like very, very difficult calculation. There's a whole subfield. Like there are people who specialize in lattice gauge theory. There's a reason for that, because it's like it's a whole career. You make a career out of this. It's just such a big field. And it is important because all this course did for you is not going to be helpful at all if you're asking nuclear physics questions. This whole course is about perturbation theory, only tells you about deep in the UV of QC, right? If the theory exists. The theory doesn't exist, there's an EFT anyway. But yeah, so lattice gauge theory has gone a long way. There's a long, very, very long story associated with that. I'm definitely not an expert. Yeah. Any other questions?